Where did we come from? What are we made of? And where are we going? These are the most basic and most ambitious questions we can ask. They've been asked across every civilization in history. The ancient Egyptians imagined the cosmos as a divine structure. The sky was the arched body of the goddess Nut, stretching protectively over the earth, supported by the air god Shu, while the earth itself was the god Jeb, lying beneath. Day and night were explained by Nut swallowing the sun and birthing it again at dawn. Their model was not scientific, but it reflected a profound intuition that the heavens obey patterns, that time flows cyclically, and that the sky and earth are part of a connected whole. Centuries later, the Greeks developed a more geometric idea. They proposed a two-sphere model, a stationary earth at the center, surrounded by a rotating sphere of stars, and a separate sphere for the planets. This model, though incorrect, was one of the first attempts to describe the universe in terms of consistent laws and motion, a major step toward scientific thinking. Today, we call this study cosmology, the science of the universe as a whole. It doesn't just ask what stars are made of, it asks where the universe came from, how it has changed, and what its future might be. And unlike ancient models, it's based on testable predictions and physical laws. A central idea in modern cosmology is the cosmological principle, that we do not occupy a special place, but rather on large scales, the universe looks the same in every direction, and the laws of physics are the same everywhere. We are not at the center, but we're part of the whole. And that whole is built on something deeper, space-time. Space and time are not separate things. They form a single four-dimensional structure, 3 dimensions for space and 1 for time. This idea comes from Einstein's theory of general relativity, which tells us that space-time can bend and curve depending on how much matter or energy is present. This is how gravity really works. Massive objects like stars and planets bend the fabric of space-time around them. Other objects move through this curved space, and that motion is what we perceive as gravity. It's not a force pulling us down, it's the shape of space-time guiding the paths of everything that moves. When Einstein's equations were first applied to the universe itself, they didn't describe something static, they described something that could expand. In the 1920s, astronomer Edwin Hubble confirmed this by observing that distant galaxies are moving away from us. Their light is stretched to longer wavelengths, a phenomenon called redshift. The further away a galaxy is, the faster it appears to be receding. This means the universe is getting bigger. Space itself is expanding. If we run the clock backward, it leads to a remarkable conclusion. The universe was once much smaller, denser, and hotter. This is the foundation of the Big Bang model. But this raised new questions. Why is the universe so uniform on large scales? Why does it look flat, not curved like a sphere or saddle? And why do galaxies and structures exist at all? The leading explanation is something called cosmic inflation. Inflation proposes that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, far faster than the speed of light. This rapid expansion smoothed out any irregularities and made the observable universe appear flat. It also explains how small fluctuations, tiny random differences in energy, could have been stretched out to cosmic scales. These fluctuations didn't come from nowhere. They came from quantum physics. In quantum field theory, our most precise model of how particles and forces work, every particle is actually a ripple in a field that fills all of space. Electrons, photons, and quarks are all tiny vibrations in invisible quantum fields. During inflation, one of these fields, called the inflaton field, dominated the energy of the universe. Tiny quantum fluctuations in this field were blown up to astronomical sizes. These became small variations in the density of matter, and over billions of years, gravity turned those small variations into galaxies, clusters, and everything else we see in the cosmos today. We can still see a snapshot of that early time in the cosmic microwave background, or the CMB. It's the oldest light in the universe, released when atoms first formed and light could travel freely. This was about 380,000 years after the Big Bang. The CMB carries detailed information about the early universe and confirms many of inflation's predictions. So why does cosmology matter? Because it connects the biggest questions we can ask to real testable science. It explains how the universe came to look the way it does. It gives us a framework for understanding time, space, and matter. It challenges us to go beyond what we know, into dark matter, dark energy, and the quantum foundations of reality. Cosmology isn't about speculation. It's about clarity, evidence, and scale. It shows us that we are not at the center of the universe, but we can still understand it.